Ladies and gentlemen, boys and girls, welcome to Looking Up for April of 2022. Yes, looking up. And so we are talking about galaxies this evening. Yes, great galaxies galore. It's galaxy season. Man, we have a lot of stuff for you this evening. This evening, we have a number of presenters. We've got Mike Humphrey with some big scopes and high hopes. We have Ernie Jacobs with Why It's Galaxy Season. Paul Moretti is going to be talking to us about some other wavelength telescopes. And Tim Collins, what is a light year, Tim? And of course, what's up? And we will be doing, this will be our last official looking up for the season. Yes, you did hear me right. Oh, don't cry. Oh, welcome everybody. This is our last looking up for this season. We are going to come back in November, but we do have something absolutely special for you. We will be having on May 15th a special looking up event. It will be starting at 10:30 p.m. and we will be doing something very, very special with you. We are going to be sharing with you a total lunar eclipse. Yes, a total lunar eclipse. You heard us right. May 15th. You'll be able to see it from Buffalo and Western New York as long as it's not cloudy. And we will be sharing that event with you live. Our public nights for the Buffalo Astronomical Association have resumed, and they are live events. Our next live event is our public night on May 7th. It begins at 8 p.m. or dusk. And we are out at Beaver Meadow, and I happen to lose one of my screens as I'm talking here, so you'll have to forgive me and my dings in the background here as it comes back up. But May 7th, we will be having a live public event. You can come out and join us and see us out there. We are unable to do some broadcasting there as we do this. We give it a try, but we have just some limited volunteers and such. And so in doing so, I need to move a couple of screens around as I'm talking to you. We will be doing those live events. In doing so, it was a little tough to try to get some live streams happening. So because we've got a decrease in COVID and as everybody gets more vaccinated and such, we are resuming those live events. The other live events that are happening, the Solar Saturdays at the Buffalo Museum of Science have resumed. Yes, you can join Tim Collins at the Buffalo Museum of Science on Saturdays from noon to 3 p.m. Also, Penn-Dixie's Astronomy has returned. Yes, as we partner with everybody, Penn-Dixie does is not only fossils, but they also do astronomy. And they have some fantastic events on June 25th, July 16th, and August 20th. You can certainly check their websites and their social media. They keep live and streaming with that, and we'll tell you a little bit more about that later. So, well, galaxy season, great galaxies galore. We have a few clear skies here in Western New York as well. And so we hopefully will have some excellent live views for you, but it's still a little bright outside. The sun has not set. Now that happens in summertime, but we get to enjoy it in some nice weather here in Western New York. Well, because we had such nice weather today, and since Solar Saturdays have returned at the Buffalo Museum of Science, Dan Marcus, our observatory director, was able to capture the sun. Yes, you heard me right. He captured some great images of the sun, and the sun is certainly reaching a return of activity. So it's quite interesting to see. Now, remember, never ever look at the sun directly with a telescope. You need specialized filters on it or a specialized telescope. And Paul may even tell us about some of those other wavelength telescopes. So I'm going to send it over to Dan Marcus, who's actually got a sharing of his image of the sun. Dan, go ahead and take it away. Oop, and Dan, you're muted, so you do have to unmute yourself when you share your screen. We are hearing Dan Marcus. Will take a second to unmute himself as he's doing so. It takes a few seconds to get used to it. So there you go, Dan. Go ahead. Tell us about the image we're seeing.
Too many screens. What we're looking at the sun here is we're looking at a bunch of sunspots in the sun. These sunspots are naked eye. If you happen to have your solar eclipse glasses hanging around the last solar eclipse, you'll be able to actually see little tiny dots in the sun. If you happen to have a telescope that's got a proper solar filter, you'll be able to make out some detail on it. This is in white light. I happen to be able to take a picture in H alpha, which you'll be able to see at the Buffalo Museum of Science. Since they have a nice hydrogen alpha solar scope up there, this is what it looks like in the wavelength of hydrogen alpha. You can make out the prominences hanging off the edge. These little black lines here are actually filaments. They're magnetic connections between the spots. And this is what it looked like today as it was setting between the trees as I was just getting set up out here at the observatory. The seeing is really terrible when it's that low on the horizon, and seeing at sunset of the sun is not the best views. But you can see the spots have changed position. They're a little farther to the left, and we now have a sunspot that's coming around. Should look pretty good if you happen to see the Museum of Science next week on Saturday. This spot should be close to the center of the sun. So that's it for the solar viewing, and I'll pass that back.
All right, that's really, really outstanding. So solar activity is happening. The total lunar eclipses are happening. Live events are returning. Boy, this is certainly an exciting time. And so I want to say a quick thank you for everybody who's joining us, and give a shout out. If you do have questions, you can post it in our Facebook Live event. I want to say hi to Don and to Steve. Let's see. And it looks like I have Tony here. So certainly love to see you join us here on our Facebook Live event and our last looking up of the summer season as we return in winter. Now, as always, we run in sometimes into technical difficulties, but that's okay. We know how to go with the fly here. So our president, Mike Humphrey, has some big scopes and high hopes. So he's got to do some realignment and some polar aligning. So as Mike polar aligns his big scope and his high hopes, we're actually going to jump off over to Ernie Jacobs. Now, Ernie has a wonderful presentation for us about why do we call this galaxy season? You know, great galaxies galore, but why? So off to Ernie Jacobs. Ernie, tell us, why is it galaxy season?
Well, that's going to be what we're going to try to learn in this presentation. Welcome, everybody. Let me just switch. Hopefully everybody can see my slide presentation okay. But starting in late February through May, the winter targets start to set in the west, or in some cases, some have already set. Very few targets, other than galaxies, are well placed for viewing imaging once it gets dark. It's galaxy season. So exactly what's going on? So let's take a look in Stellarium. So I'm going to bring up Stellarium here and make it full screen. So I have the night sky, all of the night sky shown here, pretty much middle of winter, December 23rd. And what I'd like you guys, I'm going to quickly go through and advance the night sky month by month till we get to tonight. And what I'd like you to do is I would like you to pay attention as the constellations move across the sky, roughly east to west, but also pay attention to what's going on with this band of stars, this cloudy band that's in the middle of the sky. The way this works is this would be, the outside line would be the horizon, and the very center of this circle would be directly straight up. So if I move to January, and I move to February, and then I'm gonna take our time back up to 9 o'clock and advance again to March and to April. Okay, hopefully you notice that these constellations start to get higher in the sky as it gets dark, and essentially moving towards the west. But I also hope you notice this motion, if you will, of the Milky Way, of our galaxy, because this is actually pretty telling as to why it's galaxy season now. So I'm going to go ahead and bring PowerPoint up. And so when we talk about apparent motion of the stars, within a single night, we have two rotations that are going on, or two motions that are going on. Within a single night, we see the apparent motion caused by the rotation of the Earth. So if you go out at 9 o'clock at night and you stay out and you watch the stars, they're going to move from east to west and march across the sky about 15 degrees per hour. And that's due to the rotation of our Earth. The second motion is orbital. And that is what we're interested in here. Because as the Earth moves around the sun in its orbit, the night side face of Earth, that point, its point of view is changing. And so when we were looking at stellarium and we saw how when we were looking kind of through the zenith, which would be like straight up in the night sky, the Milky Way, we started in the winter, the Milky Way was directly overhead. Now, it advanced, it moved further off to the west. And that literally, that's what's happening. When we are looking at the night sky in the winter, we're looking directly through the arms or disk of our galaxy. And we're looking towards the outside of our galaxy, but we're still looking through the disk, through the thin portion of the galaxy. As we get to galaxy season, as the Earth moves around the sun, now we're not looking through the disk. We're looking through, and I actually have a picture here. If this is our Milky Way galaxy, the sun is located out here in the suburbs around 27,000 light years from the center. But when we're in galaxy season in February, March, April, May, instead of looking through the arms of the galaxy, either towards the outside as it is in winter, or towards the center as we will be doing in summer, we're actually looking out and up, which for us, that provides a clear view of galaxies other than our own, things outside of our galaxy. And that's why this time of year, the only targets or the preponderance of targets that are available are galaxies. So, there's a few, if you're interested in going out observing, I know that Tim's going to do a what's up, so I'm not going to get into too much detail here. But if you've got a telescope and you want to try to do some galaxy hunting, the constellations that you want to concentrate on are Leo, Virgo, Corvus, Coma Berenices, Canis Fanatici, Bootes, and Ursa Major, which contains the Big Dipper. Now you might say, like, well, Ursa Major's up all the time. It's circumpolar. And yes, it never sets for our latitude, but it does move around the North Pole all year. And this time of year, the Ursa Major, the Big Dipper, and therefore the objects that are within it are higher up in the sky and are well placed for observing. So before I end, just a little bit about what galaxy observing might be like. So this is an image through my telescope, and observing galaxies can be a challenge. With few notable exceptions, they're typically small and faint top targets. This is where the word faint fuzzy comes from. Therefore, they're really well suited for telescopes with larger aperture and longer focal lengths. So be prepared. You're not going to see stunning images through the eyepiece with details and color with the spiral arm structure and whatnot. You're going to see faint smudges of gray, and some are going to have some definite discernible brightness in the center. And although they may appear as these faint gray smudges, they're still no less amazing to observe. The light from these objects comes from unimaginably large distances. When we're looking at some of the other objects in fall and winter and summer, for the most part, those objects are within our galaxy and within fairly close proximity to us, astronomically speaking. But when we look at galaxies through our telescope, and hopefully if we have clear views later tonight, our colleagues will be sharing with you, we'll be looking at galaxies 12 million, 30 million, 25 million light years away. And it's just mind-bending to think about it. And just like our Milky Way, each one of these little smudges are separate island universes onto their own, containing billions or hundreds of billions of stars. And combine this with the fact that we believe there's over 2 trillion of these galaxies in our universe. It blows your mind. So, this image is just a simple image. And in fact, I'm going to go ahead one slide and just to show you how many faint fuzzies are actually in this image. But it's just from my 80 millimeter telescope with just 45 minutes of exposure. And this field of view is about 2.5 degrees by 1.5 degrees. And so I hope you give this idea of just like how many galaxies are jam-packed into this area. Anyway, if this stokes your curiosity, if you find this fascinating and interesting, I suggest you learn about the Hubble Deep Field or the Hubble Ultra Deep Field series of images, because that will truly blow your mind. And with having said that, I don't think I have anything else. I'm going to go ahead and stop my share. I don't know if any questions came in during that presentation.
Well, Ernie, I don't see any particular questions here in Facebook Live, but I do have, humans can't even grasp the distances involved. They are beyond description. It really is absolutely amazing.
Although Tim's going to try to give us a little help in that regard later.
Ah, yes. So everything leads into something else. So as I say, everything leads into something else. I'm posting on Facebook Live right now. Let's see. There we go. Let me see if I can share this with the folks. And that's a link to the Buffalo Astronomical Association where you can become a member. Certainly help us support our outreach, help support spread this message to people, help bring up looking up to everybody. Yes, we do like sharing this. But yes, it does cost us a little bit. So any little bit that you can do is will help us. You can join, become a member. You can also donate to the Buffalo Astronomical Association. Of course, you can donate or join at the Penn-Dixie, at the Fossil and Nature Preserve, the Buffalo Audubon Society, who are our hosts for our observatory. Also the Buffalo Museum of Science. Certainly, we love supporting science in our community, science, technology, engineering, arts, and math. Yes, all together. Certainly outstanding stuff. Now, Mike Humphrey has polar aligned for us, but before we share with you my image of the Andromeda Galaxy, one of the closest galaxies to us, one of the larger ones. No, this is not a Hubble image. This is an actual image I took. I happened to take this particular image at Cherry Springs State Park. And so I figured I'd share that with you. That is after a little bit of processing. That is several hours of integration. But it really is outstanding what you can see with digitally assisted astronomy or astrophotography. Well, Mike Humphrey, our president, has certainly done a lot of work and has gotten his telescopes aligned, and he certainly does have high hopes, big scopes and high hopes. Mike Humphrey, why don't you go ahead and take it away for me?
Hey, everybody. Thank you very much. No, we had a little bit of an issue. I think we've got it resolved. And it's funny how everything works together. What I'm going to do is share my screen real quick.
Hey, Mike, if you have 2 audios on there, you may want to mute one of them for me because I'm getting a little bit of feedback. So if you could do that, that would be great.
Absolutely. How's that? Okay, and we should just be seeing one screen, is that correct? Or are you seeing, all right. Big scopes and high hopes. And it's funny how things work out, because as you recall, Ernie mentioned the Hubble Deep Field, and if you look in the background of this screen, there it is. And there's a ton of stuff in there. I think there are 3 stars, and only 3 stars in this photograph.
Mike,
So
I actually think that we're seeing your
you're seeing more than one screen?
We're seeing your notes, not the actual presentation.
Okay.
So maybe you can go ahead and share your presentation. You know, folks, it certainly is a lot of fun doing these live events.
Got to
and
start
as
the
we do it.
slideshow.
So go ahead and
I
start the
did.
slideshow there, Mike. Do you have it on a different monitor possibly, and maybe share that different monitor, or maybe stop the share and restart again?
I'm going to do that.
So that happens, ladies and gentlemen. But, you know, we have a lot of fun as we do this. We put things together. We all volunteer to do these kind of things. So, Mike, why don't you go ahead and tell us again about our big scopes and high hopes, and, of course, our wonderful deep field from the Hubble Space Telescope. There you go, Mike. That's an excellent
Are we looking good this
presentation.
time?
That looks good this
Excellent.
time. All right, Mike. Thank you so much.
Excellent. Oh, I love it when things come together. And I apologize. I'm trying to get everything to work out here. And it decided not to work just about 2 minutes ago. Anyways, big scopes and high hopes. What I want to do is start off with one thing quickly, which is my typical James Webb Space Telescope update. And let's see if we've got that going here. And for some reason, that's not going. I am having a great time, guys.
Well, tell you what, Mike. So
yeah, come back to me.
Big scopes and high hopes. Well, we have high hopes. You know what?
But right now we don't have the big scopes.
Galaxy season. That's okay, Mike. So what you go ahead and stop your share for me. And
Absolutely.
what we're going to do is talk a little bit about stuff as I let Paul Moretti know that we're going to bump him up a little bit. We're going to try to go to Paul and see if we come back to Mike and if he can fill us in. We certainly understand that. You know, when we're being astronomers, we're actually being time travelers. Yes. Time travelers. I love traveling through time. Mike in Facebook certainly was nice enough to point out, think about it. 2.5 million light years away, that light just reaching us after 2.5 million years. So here we go. So our next presentation, as I'm going to bring up for you, is Paul Moretti. Paul is going to be discussing about other wavelength telescopes. And Paul, why don't you go ahead and take it away for us?
Oh, thanks so much, Dennis. I thought I'd spend some time today going over some of the other telescopes that are out there besides the ones that view things in visible light, like most of us probably have a small telescope or odd-sized telescope, and it views in what we call visible light. And although I'm not going to be talking about things that are going to be specifically about galaxies, these are about deep sky objects, and I felt that since we had the recent deployment of the James Webb Telescope, as I'm sure Mike is going to talk about, and unfortunately the demise of the Arecibo Telescope not too long ago, I thought I'd just talk about the differences between those two scopes and some of the other ones that are out there. So before I start, I need to talk about wave terms and what we're talking about when we say wavelengths and different kinds of light features, electromagnetic wavelengths. And this is just a simple graph, for example, and you see that funny symbol at the top here. This means wavelength, and a wavelength is really nothing more than the distance between two equal points on an individual wave curve. Frequency is the number of times that wave sign or wave occurs over a certain time period, and the amplitude is actually the height of that curve, as you can see on the top here. And when you put all those together, they combine it to make these different kinds of electromagnetic waves. Now, this is the electromagnetic spectrum as we pretty much know it today. And if you notice this part in the very middle here, this itsy bitsy little part is what we see with visible light, from red light all the way to purple light. But there's all this other stuff on either side here. And if you can see by this little wave chart down here, you can see that as we go into some of the what we call longer wavelengths, which are lower in frequency, which means they occur fewer times, we get things like radio waves, microwaves, and infrared waves. And when we go faster, when we have shorter wavelengths and higher frequencies, we get into some of the other kinds of light, which are ultraviolet, X-ray, and gamma. And what I'm going to do is talk about some telescopes that are out in space right now that primarily use one of these. I mean, they may have more than one type of electromagnetic wave sensor, but they're designed for maybe one type. And you know, a lot of people probably wonder, well, why do we put telescopes in outer space? I mean, we've only really been doing this since the start of the space age. Why aren't we just building bigger ones on Earth? And these are some of the reasons why. They can obviously operate 24/7 without worrying about, you know, daytime. They're not constrained by the latitude where you know, you don't have to put them at any particular latitude. You can see just about everything. They're really not affected by weather or atmosphere. And of course, they're not affected by pollution, especially light pollution. So what kind of scopes am I going to talk about? You can see there's a whole bunch here. As we all know, there's visible light. And as an example, I used the Hubble Space Telescope and we saw that great image that Mike put up. But there's also radio telescopes. As you see here, I put up Goldstone. I didn't put a picture up. I kind of truncated this presentation. And the Arecibo telescope was also a radio telescope. At the time when it was first built, it was the largest one in existence. The Chandra Observatory observes in X-ray. So you know that that's very high frequency wavelengths. Now, James Webb is primarily for infrared viewing, which is on the other side of the spectrum. And of course, we have ultraviolet light, which is for, I think the Swift gamma ray is probably the one we hear about the most. And even microwaves, you know, the Planck Observatory, and gamma rays, which is really far out in the spectrum, and the Fermi Gamma Ray Telescope likes to look in those. So what do these kind of telescopes focus on? Well, their instrumentation really is geared for the deep space objects, you know, like galaxies and things that are really way out there. Because out in deep space, that's where some of these shorter wavelengths come from, like the X-ray and gamma rays are a function mostly of deeper space. And, you know, if we're looking at the solar system, it's better to use space probes. We can put things around. Look at, geez, we've got helicopters on Mars right now. I mean, who thought that, right? But we can put other kinds of probes, you know, closer. But when we want to go and look at deep sky stuff, we have to look in the frequencies of the electromagnetic spectrum that really go towards what they represent. So I just want to use Mars for an example here. Now, the Hubble Space Telescope has I guess a resolution of 0.05 arc seconds per pixel. All right, that may sound great, but for Mars, it's really not. I mean, these other instruments down here on the Mars probes, MOLA, which is really like I guess it's an altimetry reading, Themis, which is infrared. Context is just a high resolution camera, as is HiRISE. Now look at the resolution on the HiRISE camera, 30 centimeters per pixel. That's like looking at basketballs on the ground. I mean, think about that. And of course, they all have these mass cams, which are the things which they get to show, they do selfies all the time. You know, that's what I think we see so many times is, oh, look, there's the Mars rover. Okay, so what do these guys do? These different telescopes, they may look at an object may look very different when they look through the wavelengths of these telescopes. And it helps them identify their characteristics, their compositions, and their structures. And when we look at some of these other wavelengths, we can look at the same object and they may look a little bit different. So as I said, radio telescopes, and these are the radio telescopes at Goldstone on the left. And I believe that's the Very Large Array on the right side there. And these are what they kind of look like. They're big dishes where they need to be very big to get as much radio wavelength as they can. And these are some images actually of, this is actually from Arecibo, where this image is from. And you can see how it doesn't give you a lot of detail, but it gives you a lot of information. And again, it operates 24/7. You know, it does things according to planetary or orbital characteristics. Okay, so they usually are in looking for objects in near Earth orbit or for planets and asteroids and comets. And they can actually help identify things in the ionosphere as well, I believe. Now, the next one going up for a little shorter wavelength is the microwave telescopes. And, you know, what we're looking for there is a thing called the cosmic microwave background. That's, I think, what this image is right here that you see. It helps us understand the actual age of the universe and different types of matter and energy that may be out there. So that's what we use these kinds of telescopes for. The next one, again, is the infrared telescope. And I guess the best example right now, when it finally gets operational, would be James Webb. Well, look at the two images here. They record a little bit more to do with temperature. Look at the image on the left. These are both images of the Great Nebula in Orion, but they look totally different because the image on the left is looking at the infrared image, where the image on the right is visible light. So we get to see different kinds of structures and different kinds of compositions of the exact same nebula. So Let's kind of jump over the visible light and get over to the ultraviolet. And this is a view of the sun in ultraviolet light, and it certainly looked a lot different than Dan's image of the sun now, didn't it? It's got all kinds of crazy things going on here. And it helps us identify some of the solar storms. You can see like there's some nice kind of prominence and flares and things going on all over the place here. And even the corona, as you can see, that's the kind of light stuff we see around the outside. It even looks very different in UV light. The next kind is an X-ray telescope. Now, the sources for X-rays are like black holes, supernovas, neutron stars. I mean, really deep sky, powerful stuff. But again, it helps us understand the composition and the structure. Now, this image that we have right here, and I'm going to talk a little bit more about this later on, but this is actually, I believe this is the Crab Nebula, which doesn't look anything like a visible image would look like. You can actually see something that's sort of like a pulsar or something going on in the center here, shooting out all kinds of particles and things. So the last one, or the shortest wavelength, would be gamma ray telescopes. Very high frequency, very short wavelength. And again, the Fermi telescope, it doesn't. But look at the resolution on this thing, 6 arc minutes. That's, you may say, well, that's a lot, but it's not a lot, you know, but for deep space, it's pretty good. And it helps us identify supernovas, pulsars, dark matter, all kinds of crazy stuff. And the image on the right here is visible in ultraviolet, where the image on the left is the same thing in gamma radiation. That's pretty cool. That's a gamma ray burst that you're seeing. Not the kind of thing you would probably see in visible light, certainly not like this image here. So I want to talk a little bit about composite images, because I think, Dennis, you put up a nice image, and I don't, was that a composite image that you had? Several different images. When you're looking at a single wavelength like visible light, you take several images and you kind of work them over to increase the resolution of the image. So you get a much clearer, better picture or image. But what they also do is they take multiple wavelength groups and they combine them together. Now, obviously what they have to do, because the only one that has any color would be visible light. So they assign false colors to all the other wavelengths, and then they put the image back together again. Now, the reason for this is not to really show us what the image looks like in color, because it's mostly false images or false colors, but it helps us identify the morphology. Now, morphology just means how it's made up. Again, the composition and structure. So I'm going to use the Crab Nebula as an example, because most everybody here has heard about Messier object number 1. It was first observed over 1,000 years ago, well, close to 1,000 years ago, in 1054. Its current apparent magnitude, in other words, how bright it appears from the Earth, is only 8.4, and that's pretty dim, which means we can't even see it just with our naked eye. We would need a telescope to see it. Look at how far away it is, 6,500 light years. Now, compared to galaxies, that's right next door. But compared to some of the local stars in the area, that's pretty far away. And again, it's about 6 arc minutes in size when you look up at it in the night sky. Now, remember, that was one of the resolutions on one of those telescopes, if I'm not mistaken. So this is I believe, a visible light image of the Crab Nebula taken by the, I guess it's the Hale telescope at the Mount Palomar Observatory. And this is like the classic image. You can see all kinds of different colors of nebulosity and bright lights and everything. And this is basically was a star that blew up, and that's what you're looking at here. But look at this next image. The image at the top is what we call a composite image, and that is the Crab Nebula. Now, that doesn't look anything like the previous image, does it? And what they did was they took radio waves, infrared waves, optical visual, ultraviolet, and X-ray, and they gave them all false colors that you can see at the bottom, and then recombined the image to get this image. Again, this is not what it looks like color-wise, but look at all the different structures you can see here. You can see, again, this crazy kind of pulsar-y, I don't know, neutron star thing going on in the center. We never saw that before. Different kinds of filaments coming out, which represent either infrared or ultraviolet or X-rays. And we can see how these things are expanding outward from the center, which we normally wouldn't see in visible light. So that's why we kind of make these kinds of what we call composite images using these other wavelengths to get different kinds of structural information about a lot of the deep sky objects. So for right now, I think I'll end it there, and I'll turn it back over to you, Dennis, unless there are any questions.
No questions right yet in Facebook Live, but we certainly may have some. Paul, thank you very much for a tremendous presentation about other wavelength telescopes. Now, you did ask me about my image from the Andromeda Galaxy. Was it a composite image? Actually, my image was just a stacked image. And what a stacked
That's
image
okay, yeah.
is I take multiple images of all the colors at the same time. I stack them together, and that kind of eliminates some of the noise that happens in a photograph and helps you get better resolution on the photograph. So not exactly a image like a combined image, as you said. So now we do have a little bit of discussion, and we say hello to El Paso, Texas. I hope it's warm there, or at least maybe a little bit warmer here than Western New York, although it is quite warm here. I'm actually going to check as I'm looking at this, I'm going to go out and check my telescope here and see the temperature that it is at the telescope. And right now it is still 53 degrees outside here in Western New York and reasonably clear, but it also is still light. Now, in Facebook Live, we had a little bit of discussion back there and a question from Gus. And Gus, I certainly asked the question here. It says, is the Andromeda Galaxy going to collide with the Milky Way eventually? And so I'm going to ask Ernie Jacobs to see if he can kind of throw in a little bit of insight into that. Why don't you go ahead, Ernie, and share a little bit with us?
Happy to do it. Well, Gus, I can tell you that you are absolutely correct. So you really must know your stuff there. Great job. Both galaxies will merge in about 4.5 billion years and become one giant elliptical galaxy. One thing I do want to just say, though, as when we use the term collide, you might have envisioned the two galaxies coming together and the stars bouncing off one another like billiard balls or something like that. That's not exactly the way it plays out. Galaxies are incredibly large and stars are incredibly small compared to the distance between themselves within the galaxies. So it won't be the case where the galaxies smash into one another, but they will gravitationally interact. Some star systems may be ejected, but it's more of a merger. And I think we may have some more information on that on this particular merger. So I'm going to stop talking and pass it back to Dennis.
Okay. And as we mentioned that, because it is good stuff, and we're giving Mike Humphrey a little bit more time to make sure everything is polar aligned, Tim Collins at the Buffalo Museum of Science actually has a video he can share on NASA animation. Yes, the folks over at NASA certainly support us, and we can certainly support them. We love that stuff. Tim Collins, why don't you go ahead and tell us a little bit about this and share the animation?
Okay, so yeah, this is the animation here. Just a really quick thing, but yeah, this is something we learned about through NASA. But you can see the Milky Way rotating at super speed here, and we're going to zoom out a little bit. And in the field of view, in about 7 billion years or so, here comes Triangulum and the Andromeda Galaxy, both together. And these are two galaxies, Andromeda and the Milky Way, that are actually moving toward each other. And so here comes this so-called collision. Gravity is going to play a part here as Andromeda sort of passes us and then gets drawn back in, and they're going to sweep off a bunch of stars there. So free falling stars, and there's going to kind of like be one of those giant coin funnels that you see. So that's how they're going to react, and they're going to just keep moving until finally, as Ernie mentioned, they're going to create an extra large elliptical galaxy. And you can see the year counter down in the bottom there. So things won't settle down after that until about 7.5 billion years from now. And then we will have the Andromeda Milky Way galaxy. And so that, and if you notice, Triangulum kind of drifted away there. So I just thought I'd bring that up so you can see exactly what NASA believes could happen. So a lot of great insight there from our scientist friends. So I will turn this back over to you.
Awesome. Thank you so very much, Tim. That was really, really outstanding. Great sharing. And we love spreading that information, spreading the science and such. So yes, And well, no, but we can have fun looking at all those kind of things. But because part of science is we carry on and do a lot of things in science that we may never see the end of, but we can help the future and help the people and kind of pay it forward, if I may say so. And you can go ahead and say, here we are, we're taking it to this point. Maybe you can take it from this point and take it to the next. So Gus, maybe you'll be the next scientist to be studying something with the folks at NASA. Now, Paul, we do have a question here in Facebook, and I did post it here in our private chat, but I'm going to go ahead and ask it to you as well from Andy. Oh, and by the way, it is clear down in Texas. Nitro says it's clear, but he's got a lot of light pollution. Light pollution is a problem. It's still light here in Western New York, so we're a little hard to see this, guys. So cool that his guys are clear, but Andy, do composite images require multiple kinds of telescopes to collect the different wavelength data, or is there a way to collect a different wavelengths from a single telescope? So Paul, why don't you go ahead and take that one?
That's a great question. Well, it could be one of a couple of things, a couple of ways I can answer that. It is possible to have telescopes that have enough equipment on it that are maybe in more than one wavelength. And I think some of these telescopes do, but they don't have all of these. And the particular image that I showed, each one of those 5 different wavelengths came from a different telescope. So there was a lot of, math involved to make sure the images are the same size and everything. But for the most part, a lot of times, certain telescopes are best suited for certain wavelengths. And what they'll end up doing is, in that particular case, loading 5 different images from 5 different telescopes. But some scopes, I think even Hubble, correct me if I'm wrong on this, maybe Tim, you might know, or Mike, don't they have more than one kind of wavelength scanner on some of these scopes? I'm pretty sure they do.
That's correct.
Yes, correct.
Yeah, but in order for, they may not be, I don't know. For example, like when I showed you some of those different kinds of imaging for imagers on those Mars probes. Not all the probes have all of those, but for example, the high context, the high rise, those are some of the higher resolutions, and they'll give you one kind of an image, and certainly the infrared will give you another, even daytime versus nighttime infrared. But for this particular case, to answer your question, they can be on one telescope, but a lot of times they will composite that from several different telescopes, as the image I showed is. Hope that answered your question.
Oh, it certainly did, Paul. Thank you very much for fielding that question. Another outstanding question from Andy. Now, Amy asks here, as a new sky watcher, which do you all prefer to look at? Planets, binoculars, or telescope? So I guess we can take a look at that a little bit later, because we do have Mike Humphrey coming up, who is going to be getting into some big scopes and high hopes. So the third time is absolutely the charm for Mike Humphrey. And certainly we can think about that. And the folks over in Facebook, if you do prefer looking at planets, or you look through binoculars or a telescope, it's at the planets, certainly you can go ahead and chime in there. And without further ado, Mike Humphrey, big scopes and high hopes. Take it away, Mike. Oh, Mike, you are muted. So why don't you go ahead and unmute, Mike, and we'll try that
one more time.
This
Hopefully
is the third
can see.
introduction, and it is good. Mike Humphrey,
Normally,
with
it's
big
not like
scopes.
I'm not this bad, and I don't know what's going on today. I have 2 computers here, and I'm trying out a new computer, and it decided it didn't want to cooperate. I'm trying to actually do this presentation from 2 separate computers, so hopefully everything's going to work from now on. So we have our fingers crossed. First thing I want to do, and I do this all the time, which is one of my favorite telescopes right now, is the James Webb. And we're going to do a quick update on the James Webb. If you know it, you know what it looks like, and you know that on the sunshine, it is 124 degrees Fahrenheit. On the cold side, it's minus 449 degrees Fahrenheit, which is interesting. Kind of cool over there, when you stop and think about it. And I just heard from NASA that the cool down of the Mary instrument has gotten down to 7 degrees Kelvin, which is frightfully cold. And it's almost at operating temperature. The other thing is it's on schedule for the first astro image. So if anybody goes online, and there's a couple sites right now that are advertising images from the James Webb, there are no images yet from the James Webb. In fact, there's 2 images that I have that you can take a look at. This is one. And this one came out in February. This was the first to show that the mirrors had aligned and everything. And this is the second, which is actually fantastic to show you how they've aligned, how everything has gotten together, how it's all set up. It all looks beautiful and it's ready to go. So they're doing the last stages of calibration, getting everything ready to go for that first image, which is scheduled for July 22nd. Now, one of the major things about the when you look at the Webb, this is Hubble and this is the Webb, and you notice that the mirror is huge. And this is something that happens to all of us guys. When you talk about astronomers, we have a little thing, and it's called aperture fever. These are two of my telescopes. This is an 8-inch, and right after I got the 8-inch and they started working with it and was having a great time, I went out and I bought a 10-inch. What is it? Aperture fever. It happens to all of us when we start working with telescopes, and all of a sudden you always gonna get that bigger telescope. And the thing about it is there's no known cure. The only thing you can do is temporarily go out and buy a bigger telescope. But once it hits you, you always want to get the bigger one. And it always happens to everybody. There's nothing you can do about it. We have noticed, however, that obtaining a larger telescope, scientifically, the weather will be bad for 3 weeks, and it usually gets cloudy for 3 weeks or so. As a public service announcement, I'd like to tell everyone right now that in 2024 April, please do not buy any new equipment in April. Okay, especially around the 1st of April, we don't need anybody buying anything new. I'm telling everybody right now, if you want to get something, get it now. We don't want it to be clouded for the eclipse. So one of the big things we like to talk about, the big myth with the telescopes, big telescopes magnify light. This is not true. Magnification is controlled by the eyepieces itself and whatever objects you're using to pull that light in, but not by the scope itself. What big scopes do for us is they act like a big light bucket. They can pull a lot of photons, and because of that, we're able to do more things to manipulate that light to be able to get higher resolutions. Here's an experiment. I'd like you to go out and get a couple pieces of cardboard, scissors, salt, or if you're on a low sodium diet, then you can use sand and a timer. You're going to cut a 1/4-inch hole, a 1/2-inch hole, and a 1-inch hole in a paper. Hold the paper just about a foot over a surface and pour salt or the sand through the holes. And you're going to do that for just around 30 seconds. When you get done with the 30 seconds, measure how much salt, sand, whatever it is in the pile. Now, the larger holes will obviously pass more light, just like larger telescopes, more photons. Because you're getting more photons, it allows us to do more things. Again, because we're getting that light. Remember, this whole thing is related to light. This is a diagram that I saw and I thought was very interesting, mainly because it gives you an idea. And I'm going to highlight something down here. That's a person. So that's how big a human is in compared to some of these telescopes. And what I'd like to do is just go over a couple of the scopes on here. I'm not going to go them all, mainly because there's so many here, but we can talk a little bit about what we're seeing. Now, the first thing I want to take a look at is the Xray. Now, that was in 1897. It's a refractor. It's a 40-inch. And when this one went online in 1897, it was state of the art. And everybody thought this was the biggest thing we can go. It was fantastic. And here's the Xray right there. That's how big it is compared to some of the other telescopes. Let's jump up to another one. This is the Hooker. Now, the Hooker telescope is in Mount Wilson, California. 1917, and Edwin Hubble did most of his work using this one. It's a 100-inch reflecting telescope. We're going to jump out here, and there it is. That's how big it is compared to, say, the Xrays. Hubble, obviously it's going to be on here, is located about 340 miles above the Earth. And I have two dates on here. 1990, when it was launched and first image, and people will know, and if you saw the program that we did a couple of months ago, we talked about what happened to the Hubble mirror. So when the mirror was released, it was flawed and it was horrible. It was horrendous. They did some work on it. In 1993, the images came out, and those images were fantastic. That's why there's two dates on here, the launch date and the date that it actually got great first light. Now, its mirror is 7.8 feet, and it was considered one of the largest things that we can put in space. Here is the Hubble. That's how big it is. And look right next to it, you can see the James Webb. And we're going to talk about the James Webb in a minute or two. But I want to go to Hale first. That's in Palomar. Now, again, 1949, 200-inch reflecting, and it was thought to be one of the largest telescopes that we could build. Unfortunately, or fortunately, that is not correct, mainly because other technologies start to come on place. And we're going to take a look at the Hale, which is right there. And you can compare the Hale to some of the other telescopes that we've already spoken about. Now we go to James Webb. James Webb right now is considered one of the largest things that we can put in space. The date that is going to go first light is proposed for 2022 in July, and its optical, its mirror is 21 feet. I'm going to bring this up here to show it to you. And one of the interesting things about it, and we're going to jump in this right now, is its mirror. They're using a hexagon. So why use a hexagon for a mirror? Why not use a round mirror? Well, obviously, if you're launching it this big, it had to be folded up. And they needed to get a shape